Okay.
Namaste, buongiorno, good morning, ni hao, I don't know what else, guten Morgen. So I'm Kishore Trivedi, and I want to tell you a little bit about reliability and availability of hardware software systems. And my co-author on many of the works is also on Andrea Bobbio. So you can ask all the difficult questions to him, only simple questions to me, all right? So let's see if the slides move. Okay, so the objectives of this tutorial is to provide an overview and state-of-the-art of analytic methods for reliability and availability assessment of both hardware and software systems. And in the process, we will provide you some real-life examples that show the use of these methods in practice. And to provide, at the end, some current challenges faced in such assessment projects. So some of the PhD students might get some good ideas of what to work on from our perspective. And this is an attempt to summarize a book that Andrea Bobbio and I published in 2017. It is so-called Green Book. Well, my books are all known by the colors of their cover. So this is the Green Book. So in that process, but before I go on, these are a couple of announcements. Those who are students, you may get a certificate for participation in this course. And for that, you have to fill this Google form. And also on Friday, as was mentioned by Danilo, that there is a Meet the Star event for PhD students and postdocs with the keynotes and several other important people. So you might want to take advantage of that. Those are the two announcements from the conference organizers. Now, the tutorial itself, I will start with some motivation and introduction. And then we will jump into the core topic, namely reliability and availability assessment. And there we will provide to you all the methods that people use in practice. And this will all be illustrated through several real-world examples of hardware, software, or combined hardware software systems that some of us have actually worked on ourselves with industry. And then I'll provide some concluding remarks. And I will also give you some references. I don't know whether there is any provision for uploading the slides on the conference website, but I'm very happy to provide
Yes, we can.
slides to Danilo, and he can then upload them if he wishes to. And so motivation-wise, it is clear that we use computer and communication systems in just about everything we do these days. And so we expect them to highly reliable, highly dependable, and so on. But in this process, let me just start with some terminology. So reliability is often used in a very generic sense as an umbrella term, that system is highly reliable. But reliability also is used as a precisely defined mathematical function, as we will see. So to remove the confusion, IFIP Working Group 10.4, of which I'm a member, proposed dependability as an umbrella term and kept reliability as a well-defined mathematical function. So given that terminology, we start with dependability, which is the umbrella term that says that trustworthiness of a system such that reliance can justifiably be placed on the service it delivers. And then they provided a tree of dependability. And this tree has three legs. The bottommost leg here says that what are the threats to dependability? What are the causes for dependability to be bad? And these are classified into three: faults, errors, and failures, and we will define them very soon. Then the next question is, what are the means to achieve high dependability? And they provide four different ideas: fault avoidance or fault prevention, fault removal, fault tolerance, and fault forecasting. We will be talking about these two, fault tolerance and fault forecasting. Fault prevention basically says that you want to use methods that will, in the first place, have fewer faults in your system. So in the software context, for example, this is using a very good software architecture or very good software development system and so on, so that you have as few bugs as possible in your software system. Fault removal says that in spite of all that effort, there will be some faults remaining, some bugs remaining in your system or software. And so there is systematic testing and removal of faults that is advocated there. And in spite of all that, the current day systems do have bugs or faults during operation, and that is where fault tolerance come into being. And fault forecasting is a way to predict what is the reliability and availability of the system. So these are the two things we'll be concentrating on today. And the third leg of dependability tree says, what are the different ways of assessing the dependability of your system? And these are attributes. And two key attributes are reliability and availability that we'll be dealing with. We are not concentrating on safety and maintainability here, but only these two. So given that introduction, first difference between reliability and availability. Reliability refers to failure-free system operation during an entire interval. And so, for example, a flight control system of an aircraft, you are interested in no system failure occurring during the entire flight. By contrast, availability refers to failure-free system operation at a given instant of time. And it is possible to combine these two under the notion of interval reliability, but this is a point at which issue on which a lot more research is necessary. We don't know enough about how to compute interval reliability. We know in some simple cases, and most people in practice are not aware. So, but in the future, I expect a lot more emphasis on interval reliability as opposed to simply reliability or availability. Now, we talked about faults, errors, and failures as the definitional terms. So to clarify what they mean, a failure is said to occur when the delivered service no longer complies with the expected or desired service. So this is at the interface, at the output of the system. And error is said to occur when a part of the system state has some wrong bits, which may lead to failure. And fault is the overall cause of error and subsequent failure. So you may say faults are the causes of errors, and errors may lead to failures. So for example, for a software system, a bug is a fault. Software bug is a fault. And that bug by itself is not necessarily a problem until and unless it is exercised by some inputs that generate some wrong bits internally in your software system. And this is an error. Error by itself may not be a problem until and unless it propagates to the output, generating a wrong answer that the user sees. So that's a failure. So fault is different from error, from failure. Now, faults may be classified into physical or hardware faults, design faults, or interaction faults. In a context of a network, maybe a node fault or a link fault. In the context of a computer system or a networking system, the fault may be hardware fault or a software fault or even a human fault. In our discussion today, we are only concerned with hardware and software. We are not explicitly considering human faults. And within hardware context, faults may be classified as permanent, intermittent, and transient. And within the software context, the bugs have been classified more recently into Bohr bugs, Mendel bugs, and aging-related bugs. This will not be the main topic here today, but those of you who are interested, next Tuesday, that is on 16th November, I'm doing a webinar under IEEE Transactional Reliability on this topic. Now, that is a classification of faults. Now we classify failures. Failures can be omission failure in the sense that when you expect an answer, you don't get an answer. That's an omission failure. And that may occur because your system has crashed, or within your program, there's an infinite loop. So program never terminates to give an answer. Now, this is one kind of failure, but it is possible that you get an answer, but the answer is incorrect. And this kind of failure is response failure or value failure. Now, there is a third kind of failure that you do get an answer, you get a correct answer, but the answer may be too late. And such a failure may be a timing failure. And this is important perhaps in the real-time, so-called real-time systems. And these kinds of failures can also have been also called performance failure or dynamic failure. The failures may also be classified into safe versus unsafe. And failures may also be classified, particularly in the security context, into breach of confidentiality, breach of integrity, or loss of use. We are not going to talk about safety and security in this talk. So continuing with basic definitions, now we talk about reliability. Reliability sometimes is simply a probability of being successful or not once you ask for something. And that is called one-shot reliability. But more commonly, reliability is defined as a time-dependent function, R of t. And so to define that, let's suppose that you start a system in operation at some time 0, and system will eventually fail. You know that everything fails. And time to failure is not fixed in advance. So we'll consider it as a random variable. So this is TTF, time to failure, or lifetime random variable of the system. Let's call it X. Now, given a random variable X, there is the notion of its distribution function, also called cumulative distribution function. F, let's call it capital F of F at T. And by definition, from any probability text, this is the probability that X is less than equal to T. Now, complement probability is the reliability. RT is the probability that the time to failure random variable takes a value greater than T. That means failure has not occurred until time T. So there is simply 1 minus F of T. And so reliability is the probability that system has not failed until time T. It is the complementary distribution function of the time to failure random variable. And from the reliability, we can also compute the mean time to system failure, the expected value of the random variable X, which by definition is T multiplied by the density function of T integrated from 0 to infinity. But we can also derive it as an integral under the reliability curve. Integral from 0 to infinity under the entire reliability curve. But oftentimes in practice there is confusion, and I emphasize that to make a clear distinction between time to failure, which is the random variable, RT, which is the probability that the random variable takes a value greater than T, and MTTF, mean time to failure, which is the expected value of this random variable, which is also the area under the reliability curve. And a reliability curve may look like this. Generally, at time 0, system is, when you put in operation, system is assumed to be functioning properly. So reliability is 1, and slowly but surely reliability drops down until it hits 0. So the R at 0, at time 0, is usually considered to be 1. And the limiting value of R as T approaches infinity is 0. And the RT is a non-increasing function of T normally. It is also possible to allow for the possibility that when you start the system operation, the system is not functioning properly. And in that case, we will start, R of T will be 1 minus Q, where little q is the probability that the system has failed at time 0. It is in the failed status at time 0, in which case R of 0 will be 1 minus Q, and R of T will still be approaching 0 as T approaches infinity. And So Q is the probability that the item is defective to begin with. And this kind of situation often arises, and the corresponding distribution function can be written like that. And this often arises I'm sorry that my animation is in the wrong order. Dead on arrival, that is system, and sometimes this is called a lemon. When you buy something, it is bad to begin with, that is allowed by the previous expression. And this can be accommodated in non-state space models if the tool allows such distribution functions with so-called mass at origin. And this is allowed in our tool Sharp that I may mention a little bit later on. And it is also important in so-called phase mission models. And this can be easily incorporated in Markov models that we'll be talking about by properly assigning the initial state probabilities to the components. Now, let's, having talked about reliability, now we talk about availability. So let's suppose that we keep track of an indicator random variable of the system that takes the value 1 when system is up and value 0 when system is down. So let's suppose that system starts in an up state to begin with, and after some time it's almost surely going to fail. And after failure, let's suppose that system is restored after some time to the fully up state, and then it goes through the cycle up and down, up and down, up and down. And this is a sample path of the trajectory of the system. And there can be another sample path at another point in time and so on. So now the definition of availability, or so-called instantaneous availability, is that the probability the system is working at time t. And from the figure in the last slide, the availability at time t becomes the probability that the IT, or indicator random variable of the system, takes the value 1 at time t. And this is sometimes called pointwise availability, instantaneous availability, or transient availability. And we can ask for AT at any time point t greater than or equal to 0. And in particular, and of course, I mentioned earlier that RT and AT can be combined into interval reliability. And I'm not going to talk much more about it, except that interval reliability was originally defined in a paper by Barlow and Hunter in 1961 that combines the notion of instantaneous availability and reliability. And the idea is that a system is expected to be available at time t when I need it, and as long as it is needed for, say, time tau units. So both these ideas are combined together. This idea is developed a little bit further in a paper that I've written with a graduate student at that time, Daji Wang. It's in not a very well-known journal. Nevertheless, it is a very important paper, I think. So somebody who wants to explore this further should take either that one up or some of the things we have written in the book, the Green Book, as well as a couple of papers that carry that concept in a practical context. But this is a very, very important topic that you might find a lot of work to do on and get several important papers and possibly PhD thesis. Now, coming back to the notion of just availability, the instantaneous availability can be taken a limit t approaches infinity, and then what you get is limiting or steady state availability, or normally when you say availability in practice, that's what you mean. This is the long-term probability that the system is available. And under very general assumptions, this can be shown to be mean time to failure divided by mean time to failure plus mean time to repair, steady state availability expression. And where MTTF is the system mean time to failure, and MTTR is system mean time to recover or restore or repair, whatever you want to call it. And this T time to repair may consist of many phases in practice. So this formula holds without any distributional assumptions. So time to failure distribution may be Weibull or whatever. Time to repair distribution may be log normal or whatever. And as it is, it applies only to systems without fault tolerance. If you want to apply it to system with fault tolerance, then we have to very carefully define what is meant by MTTF and what is meant by MTTR. And these are taken to be equivalent mean time to failure, and equivalent mean time to repair. And these have been precisely defined, and I've given you several references from my blue book, from the original paper in IEEE Transaction on Reliability, and from the green book. So you can find information about this notion of equivalent failure, equivalent mean time to failure and equivalent mean time to repair. Then this formula applies to any system, even with fault tolerance. Now, from the availability, we can get this steady state unavailability, which is 1 minus ASS. You multiply that by 8760 and 60, then you get downtime, steady state downtime actually in minutes per year. And so in practice, availability is defined either by the number of nines in the steady state availability or downtime minutes per year. So for example, if you want to claim that your system has 5 nines availability, which means that ASS is 0.99999 XXS afterwards, this means 5 nines availability. That translates into, by above expression, 5.26 minutes of downtime in a whole year. And similarly, 4 nines availability will translate into 52.56 minutes of annual downtime. Now, so let's look at, somebody looked at the real life data, and they found that 49% of Fortune 500 companies experience at least 1.6 hours of downtime per week. When we put that into downtime or availability, we find that this particular data tells you that the real systems have 2 nines availability, not 5 nines and 6 nines that they claim in practice. And this can be corroborated by many incidences of major companies that you find major downtimes in iCloud, in Amazon, in Microsoft, in Google, in Facebook. And this continues over the years, Microsoft, Google, Amazon. And so and more recent examples, in commercial aircrafts, Boeing 737 MAX software problem everybody has heard of, and people died because of these problems. So failures and downtimes lead to loss of reputation, they lead to loss of revenue, and they lead to possible loss of life and possible loss of mission. So we need methods that reduce system failures in the first place and reduce the downtime that results from these failures in the second place, and which may be contributed by hardware, software, or human beings. And correspondingly, we need methods for assessing system reliability and availability, and to help find bottlenecks so that if you need to improve system reliability or availability, where should you put the effort, most effort, that will be effective in improving your system reliability or availability. So these are the 2 topics of interest, and I will quickly go through this topic and concentrate on the second topic, which is the objective of this tutorial. So again, sometimes the animation doesn't quite work right. So methods of improving dependability. First idea is fault avoidance or fault prevention, we called it earlier, which means you employ highly reliable components, or in the case of software, use methods that will lead to as few bugs as possible. But then you find that bugs are always there, whether you like it or not, in real life software systems or even hardware systems. So you test and find and fix the bugs, fault removal. But even after all the effort on testing and removing, we find that software and systems in practice do have the potential for failures, and therefore we need to introduce fault tolerance. And primary methods of fault tolerance is utilizing redundancy. And correspondingly, as we said, we need to be able to forecast when the failures might occur, and also find bottlenecks so that at design time you can reduce the possible failures in the future. at operational time, you should be able to predict when failures may occur and then use preventive maintenance techniques at operational time. So these are the ideas that people have been playing with to try to improve dependability. And as I said, we are primarily concerned with fault tolerance and assessment of reliability and availability. And fault tolerance depends basically on redundancy, using more components than necessary. And there are three types of redundancy: coding redundancy, time redundancy, and using multiple components, more components than required for the from the performance perspective. And so coding redundancy, I'm not going to concentrate on that, but just to tell you that there are different types of codes available. Hamming code is an error correcting code that has been in use for maybe more than 50 years. There is Reed-Muller and Reed-Solomon code. I've heard that Reed-Solomon code is being used now in the quantum computing context. CRC codes are often used in message transmission through the internet. The time redundancy says that if at first you don't succeed, try and try again. So at the bottom level, oftentimes the CPU will retry an instruction if it doesn't work right in the first time. Similarly, you often restart a process after it failures. There is something called checkpoint restart, and in the message transmission in the internet, until acknowledgement is received, they will keep retransmitting the message over and over. So this is called time redundancy. And then the last kind of redundancy, but before we go on further time redundancy wise, time redundancy is a time-honored concept with respect to tolerating hardware transient faults due to alpha particles and so on. But now it is recognized that time redundancy, retry, restart, and reboot, can also be used to recover from software failures. And more on this later in this talk, but much more so in the next Tuesday's webinar from IEEE Reliability Society. Multiple redundant component is the third method of redundance. And so the standard ways of organizing these multiple components, redundant components, the most common thing is parallel redundancy, such as, for example, you employ in aircraft engines. One engine might be enough to fly the plane, but you still employ two engines, and this is parallel redundancy. Similarly, more generally, you can have K out of N redundancy. So, for example, 2 out of 3 is very common. These are both static redundancy in the sense that no action needs to be taken in time during operation in order to utilize the redundancy. By contrast, there is something called standby redundancy or dynamic redundancy. And the most typical example of this is a spare tire in your car. In this case, the actions have to be taken during operation time to detect, to reconfigure the system, to employ the redundant components. And the redundant components, standby redundant components, may be in a cold status, warm status, or hot status. We are not going to explore this in great detail, but I want to give you an overall idea of types of redundancy. On top of that, the components that are used, redundant components, are they statistically identical or statistically non-identical? We will explore a little bit of this in a few minutes. Now, I don't know whether I should be if there are questions, I will try to monitor the chat box, but are there any questions so far? All right. Everybody listening, or people are asleep?
No, I mean, I think it's clear. Thank you, Kishore.
Okay, good.
Thank you.
All right. Some more notes here. In hardware redundancy, normally statistically identical components are used, though not always. In software, it was thought in 1970s that identical redundant copies of software will not be useful for fault tolerance, because if one copy has the bugs, the second copy is exactly the same bugs. And so they came up with the notion of design diversity, and we will mention a little bit more, but much more of this in next week's webinar if you're interested. So classical techniques of software fault tolerance built around design diversity. So you give the same specifications to 2 or more different teams, and they build software systems with the same specifications, but hopefully with a different algorithm, different language, different development system, so that the versions that are produced are diverse versions. They will have different faults. So if one version fails, the second version may not fail in the same set of inputs. That was the idea of design diversity. And the design diversity, there are 2 principal methods of using design diversity. One is called recovery block, and the other is called end-version programming. And in our classification earlier, recovery block is like standby redundancy, and end-version programming is like K out of N or parallel redundancy. It is now recognized that failover to identical software copy does help in recovering after software failures. More on this later. Now, the last point is with respect to maintenance. And maintenance can be reactive, that is after the failure occurs, or it can be proactive, that is preventive or scheduled, whereas reactive or unscheduled. And I don't want to go in details of this, but reactive maintenance, there can be many stages, and that it can be escalated. We might come back to that a little bit. But the key point is the preventive maintenance can be time-based or condition-based. For example, if you changing oil in a car, in the older types of cars, non-electric vehicles, you can say after every so many kilometers, I will change the oil, or you can check the condition of the oil using the dipstick. If the oil is dirty or low, then only you change the oil. So these are 2 different principal methods of doing preventive maintenance. And it is also known that preventive maintenance is only useful if there is aging in the system, whether hardware or software. So some more notes. Conventional wisdom is that unlike hardware, software does not age. So preventive maintenance does not help in software systems. That is the conventional wisdom. Well, I got news for you. Since 1995, it has been recognized that software does age, and preventive maintenance in the context of software system has been found to be useful. And this is called software rejuvenation. And if you want to know more about this, there is a whole monograph on this topic that we have recently written, Handbook of Software Aging and Rejuvenation. And this is called an orange book. Remember, each of my book has to have a color. And this color, at least stripe here, is orange. So this is the orange book. So what we now have covered briefly is the methods that reduce system failures and reduce downtime due to these failures. And now we will concentrate on how to assess system reliability and availability. We will not be paying attention to bottleneck detection, but these methods are also available in the books that we mentioned. So if you are interested in quantitative assessment of system reliability and availability, what are the different techniques that are available at our disposal? Well, simplest thing to do is observe the system and get data from the observations. And this method then is maybe called black box. We are not looking inside the system as to what it is composed of, and we are simply collecting the data. So data-driven method. And so we collect the measurement data of times to failure, I assume, and then we apply some statistical inference techniques to assess whether the system, what level of reliability system has or availability system has. So system is treated as a monolithic whole without explicitly taking its internal structure into account. And of course, this is very expensive, especially for ultra reliable system. When you are assessing the probability of failure of 10 to the minus 9, for example, this will take a huge amount of data to be able to get any statistically significant result. And furthermore, if the system is under design, this is not applicable at all. Also, I want to point out that there are methods known that reduce the time of observation, and these methods are called ALT, accelerated life testing. And but in any case, with all the methods available today, this approach is generally applicable to small systems that are not very highly reliable, and certainly not feasible for system under design or development because you don't have the system available for observation. So the alternative method then, which is what we are going to talk about, may be called white box or model driven, where no data is available for the system as a whole. What we do is we develop a stochastic model, probability model, such as reliability block diagrams, fault tree, Markov chain, etc., which is constructed based on the known internal structure of the system. That's why this is a white box model. That is its components and their characteristics and interactions between these components. And thus we are deriving the behavior of ensembles or combinations of components that form a system from first principles of probability theory. And this can be then used to analyze system with many interacting and interdependent components, which is what we see in life today. But in order to get answers from these probability models, we need input parameters about the components and of the subsystems. So in effect, we are combining the two approaches where we use black box approach at the subsystem or component level, and we use the white box approach at the system level. But I'm only going to talk about the system level approach today. There can be a separate tutorial on the black box approach at the subsystem level. Thus, actually, in practice, we are using a combined data plus model-driven approach to assess system reliability and availability. Now, I think in interest of time, I'm going to skip this slide. So we'll now start talking about the types of probability models that we have used in practice to solve the reliability and availability models of real-life systems. So overall picture that we have so far is that for quantitative reliability and availability assessment, one approach is data-driven or black box, which may be called error, failure, or recovery data analytics. The second approach is model-driven. So we develop a model, and that model, if you are lucky, can be solved using analytic means, or if the model is so complex that we are not able to, then we go to discrete event simulation. And in the future, I would like to see more and more hybrid approaches where part of the system model can be solved using analytic means and part using simulation, and they interact with each other. Now, whenever people talk about analytic methods of solution, they generally have this closed form solution in mind, closed form formula. Well, this is possible only for very limited either small or highly structured systems. More often than that, real life problems will not be like that, but it is possible quite often to develop the underlying analytic equations, and solve the equations numerically via a software package or a tool. And in my experience, this approach to analytic models, which may be called analytic numeric solutions, is not as well utilized as it could be. And people jump unnecessarily too much to discrete event simulation. So my life has been devoted to this idea that numerical solution of analytic models, and this is a much more useful method than perhaps discrete event simulation, because this can apply to a much larger class of problems than what people think. And if only that is not applicable, then you go to discrete event simulation. So we'll be talking about primarily this approach. And within the analytic methods, we divide them into 4 groups. I don't know whether I will have a chance to cover all 4. The first group, the simplest ones, we call them non-state space methods. And then we will go to state space methods. And finally, the real way of solving real life problems are hierarchical composition and fixed point iteration. So let's jump into the non-state space methods for solving reliability and availability problems. And non-state space methods can be further classified into series parallel reliability block diagrams, which we abbreviated as to RBD, fault trees of two types, fault trees without repeated events and fault trees with repeated events, and reliability graphs, which are nothing but non-series parallel reliability block diagrams. So we'll go through this in sequence very quickly. And of course, at the base, we will assume that all components are binary in nature, that is either up or down or failed or non-failed. But in general, this can be extended. All these methods can be extended to multi-state components and so-called phase mission systems. All this you find in the Green Book. I don't have time to go through all these different types of extensions. Now, just to start with some real-life example, in around 1999, Cisco approached me to do an availability analysis of one of their routers because there was a competition from Juniper that seemed to be too big for Cisco to handle or consider. And so they wanted to show that their system has higher availability than the competition from Juniper. And they wanted an independent person to say this. And so they invited me to do an availability analysis of Cisco router 12,000 with Juniper router. And so what at the top level, I found that after detailed analysis, that the Cisco router 12,000 can be modeled as a reliability block diagram with this many different components or subsystems in series. Now it turns out that the red indicates a submodel. And so this is actually going to be hierarchical. But at this level, at the top level, it is a simple series reliability block diagram. And similarly, Juniper competition AM20 router also ended up being a series reliability block diagram. And then a detailed analysis was conducted and submitted to Cisco as a report. And it turned out that the answer was that they are about the same in availability, and therefore Cisco didn't publicize this particular report very much. But otherwise, if I had discovered that Cisco was more available than Juniper, they would have put it on a top level in their website. And then around the same time, maybe a year or two later, Sun Microsystems invited me to help them do the availability analysis of their high availability system platform. And what we found again at the top level, the system could be modeled by a series parallel reliability block diagram. There are parallel components here, as well as K out of N, 4 out of 7. Remember, I talked about 4 out of 7 parallel redundancy and K out of 7 type of redundancy. And once again, actually, this is going to be a hierarchical model, and we'll come back to this, where these are developed separately, the ones in red. So just to summarize this part, series parallel reliability block diagrams, assuming statistical independence of failures and repairs, reliabilities multiply for series blocks in series, and unreliabilities multiply for blocks in parallel, and blocks in K out of N have a very simple binomial formula for their reliability. And so this can be easily programmed in any tool and has been programmed in many tools. Now, occasionally, though, you do need something a little more involved. So, for example, here in the Cisco, in the Sun Microsystems case, these satellite cards, they're identical, statistically identical, and this 4 out of 7 or K out of N identical case. But occasionally, as we see in this particular picture, this is problem 4.22 from our Green Book, where this is a real life problem in which there's a 3 out of 4 combination here, except that these 3 are identical, but the 4th line is different. So non-identical 3 out of 4 is necessary to be developed. And so we wrote a formula for it, for the non-identical 3 out of 4, K out of N, in our green book that you can find. Very simple formula was developed for that. So that summarizes the state of the art, if you will, on this topic of series parallel reliability block diagrams. Now, if you are a computer engineer or a communications engineer, you tend to use block diagrams. But if you work in nuclear industry or aerospace industry, you use something different called a fault tree. And so fault trees may be thought of as a pessimist paradigm as opposed to reliability block diagram, which is considered an optimist paradigm. Why? Because in the reliability block diagram, you're looking for a condition under which system is working properly, whereas in a fault tree, we are worrying about conditions under which system has failed. So components are represented as leaves or terminal nodes, and internal nodes are logic gates such as and, or, etc. And the root node or the top node of the tree indicates system failure. And components of subsystems in series are connected with OR gates. Components of subsystems in parallel are connected with AND gates. And failure of a component or subsystem causes the corresponding input to the gate to become true. And whenever the output of the topmost gate is true, the system is considered failed. I know this is a lot to consider in a quick session, but what I'm trying to negotiate right now is to do a full 2-week course on system reliability and availability, perhaps somewhere in Italy this summer. And so people can actually get the whole range of ideas of how to do this in practice. So this is an example of a fault tree that General Electric supplied to me that they use for truck AC6000. And so this is actually a very simple system with 4 subsystems. And there's an OR gate that says, basically says that any one of the subsystem failing, system fails. And very simple to analyze this, just like a reliability block diagram. So fault trees like this are equivalent to reliability block diagrams that we considered. But fault trees can get more interesting, more complicated. And this is a fault tree, again, supplied by General Electric to me for their equipment ventilation system. And what this fault tree has is something called a repeated event. So for example, this event and this event are exactly the same event. And this repeated event is indicated by the inverted triangle in the sharp context, our tool sharp. Similarly, this event AB and this event AB is exactly the same event. So this kind of fault trees are more powerful. They are called fault trees with repeated events. But at the same time, of course, the solution method for these kinds of fault trees get more complex. And so these are fault trees with repeated events, which occur all the time in practice. And this is an example of a fault tree that we developed for IBM Blade Center. And so they get much more interesting with lots of events and lots of repeated events. And so in order to deal with such more complex system models, we need software packages that have programmed the solution methods. And one such software package that we developed is called SHARP. It stands for Symbolic Hierarchical Automated Reliability and Performance Evaluator. And it's a stochastic modeling tool installed maybe over 1,000, maybe it has 1,200 now. I don't keep a very good count, both companies and universities. And it has been ported to most architectures and operating systems. And that it is used for education, research, and engineering practice. And that many of the users in companies are listed here, Boeing, and fairly consistently, and many other potential users at many other companies. Most recent ones is Honda, for example. GE has been consistently using for many years, and so on. And to get more information about this, there is this particular web page that you can look at. Currently, the GUI is being redone by a student in Beihang University in China. But there is a lot more possibilities of enhancing the algorithms and improving the GUI and so on. So there may be more projects, that joint projects with people in Europe and China and so on to try to do this. And it is a core of Boeing's internal tool called IRAP. So fault trees, major characteristics, fault trees without repeated events can be solved very easily in polynomial time, like the series parallel reliability block diagrams. But fault trees with repeated events, theoretical complexity is exponentially the number of components. And the methods that are available, one is called factoring or conditioning. Second is find all minimal cut sets and then use something called sum of disjoint products to compute reliability or availability. And the third method is based on what is called BDD, binary decision diagrams. All these are fully developed in our green book. In practice, we can solve fault trees with thousands of components. And solution time for very large fault trees, we have investigated in one of our efforts. And here, the number of leaves or the number of components can be up to 100,000, for example. And using the factoring or SDP, we are able to solve those problems within a reasonable computing time. In particular case, the BDD didn't go beyond 60,000, but in general, BDD is better. It depends on the actual fault tree. In this particular case, factoring was better, and second was BDD, and third was SDP. Fault trees have been extended to include variety of different gates, such as NOT gates, exclusive OR gate, priority AND gate, etc., etc. And some of these gates are called static gates, and some of these gates are called dynamic gates. The last non-state space model type that I want to cover is called reliability graph, or relgraph for short. So it consists of a set of nodes and edges, and edge represents components that can fail, whereas and then nodes don't fail in this particular formalism. There is a special node called source node, another special node called target node. They are also called sink or terminal nodes. And the system is said to fail when there is no path from source to terminal along which all components are functioning properly. And so this can be viewed as nothing but a non-series parallel reliability block diagram. And this is a very well-known problem in the operations research or applied probability or reliability theory. It is also called ST connectedness problem or network reliability problem. And solution methods for relgraph consists of finding all min paths followed by SDP, sum of disjoint products, or binary decision diagrams based methods, or factoring or conditioning methods. And yet another is Monte Carlo method, and there is again a lot of work on that too. These first two methods have been implemented in SHARP. And I'll give you an example from the Green Book 5.8, problem 5.8, where there is a water distribution network, and these are the pipes. And so pipe 1 takes you from node 1 to node 3, etc. And the source node is 1 and the terminal node is 2. And so this is a relgraph, and this can be input to SHARP very simply by this particular language. And you can ask SHARP for all the min paths, or you can ask SHARP for the system reliability. Here I've assumed that the probability of each pipe failing is 0.1. You can change it and you can do a lot of other things there. And here SHARP tells me the min paths. There are 4 min paths from the source to terminal, and the corresponding system reliability is turning out to be this and so on. Now, it turns out that reliability analysis of each major subsystem of a commercial airplane needs to be carried out and presented to the Federal Aviation Administration for certification. And so I bring you a real world example from Boeing Commercial Airplane Company. Around 2007, they had a new plane called 787, Boeing 787 Dreamliner. And for the certification of this plane, they needed to do the reliability analysis of each subsystem. Now, most of the subsystems are the improved versions or modified versions of subsystems in earlier planes. So what they normally do is take the model that they had used for certification of an earlier plane and modify that model for the new plane, and then do the reliability analysis and go on from there. Occasionally, however, there is an entirely new subsystem. And there was an occasion in 787 that there was an entirely new subsystem, which was called current return network. And my former students are part of the Boeing reliability engineering team. So they were asked to do the reliability analysis of this new subsystem in 787. And they saw the problem could be cast as a reliability graph that we have been talking about. And so they got very excited and they called me and I said, that makes me very happy if you are successful in using reliability graph and particularly via SHARP. As I told you, Boeing has access to SHARP via their tool called IRAP. So current return network of Boeing 787 is one such example where reliability graph could be used. And several of my former students are in Boeing Commercial Airplane Reliability Engineering Group. So they said that the current return network can be modeled as a reliability graph like this. There is a source node, terminal node, and there are edges that can fail, which represents various subsystems in their system. And so given the probability of failure of each of these edge, I want to know what is the probability of a connection from source to terminal. That is the reliability of the current return network. So this is a well-defined problem. We have a well-defined set of solutions in SHARP. So it was thought to be very easy to get an answer. But, and solution methods implemented in SHARP, as I told you, Boeing tried to use these two solution methods, but it didn't work. It didn't work. So before I tell you what we did, let me tell you why it didn't work. So one of the methods I told you was to find all min paths, find all the paths from source to target that don't have any multiplicities. And so that's called a min path. In this particular case, the number of min paths was estimated to be 4.2 trillion. 4.2 trillion. That's a huge number. So finding all the min paths and then doing a probability of the union of all the min paths, there is no way in the world anybody can do this. This will be intractable problem. So obviously, but the problem had to be solved. So they asked me again, Boeing asked me, is there a solution to this problem? And I said, I have an idea and I can send a very good graduate student to help you out. So I sent a graduate student for 4 months equipped with this very simple idea, and turned out that we were able to solve the problem very easily. And the idea is actually very simple, finding the bounds. It turns out, and I don't have time to tell you more details of this, but computing bounds, upper and lower bounds, was possible very simply with a very few min paths and min cuts. And so to tell you, in this particular case, our approach was to develop a new efficient algorithm for unreliability bounds rather than exact reliability. And this bound computation was very efficiently done and incorporated in SHARP. And this problem could be solved within 900 seconds of computer time. And Boeing liked the algorithm so much that they wanted to patent it. So there was a patent issued after 3 years. 2008, the work was done. 2011, the patent got issued. And we had to wait for publishing the paper. A paper got published in 2014 in European Journal of Operations Research. So this is available to anybody who want to look at the details of the algorithm. It turned out that satisfying FAA was even harder. So after this solution was done, the Boeing took it to FAA, and FAA then asked, okay, you have solved the problem. of computed the reliability, and it is acceptable, except what tool was used for solving the problem, and this is SHARP was used. Then the next question was DO's Department of Defense standard called DO 178B. Was it used in the software development for SHARP? So Boeing sends me the information about this DO 178B. I never heard of DO 178B. And so I was stuck there. So I did a mind dump of everything that we had done on SHARP development and put together a document which I called validation document, submitted to Boeing. Boeing took it to FAA, and fortunately FAA accepted that as a validation document for SHARP. Now I'm told that every new Boeing plane that has a current return network, this particular algorithm that we developed is being used to solve the problem and help in certification of for FAA. So at this point, we can quickly go through, summarize series parallel reliability block diagrams and fault trees without repeated events are equivalent, but relgraph is more powerful than the reliability block diagram since non-series parallel behavior can be accommodated. Fault trees with repeated events are even more powerful than relgraphs. And most scalable method is the bounding algorithm for relgraphs that we developed for Boeing. And this needs to be extended to fault trees, which has not been done to my knowledge. And this can be also seen in this power structure, if you will. Reliability block diagrams and fault trees without repeated events are equivalent. Reliability graph is more powerful than either. Fault trees with repeated events are more powerful. And even more powerful are the state space methods that we will next consider. So this may be a very good time for a very quick break, 5-minute break, and I'll come back after 5 minutes. You should all come back too. I hope you're not falling asleep or getting bored or anything like that.
I think, I mean, they're surviving, I think, for sure. Yeah, I mean, it's great for having the break, and we'll stop the recording now and we will restart later. Thank you, Kishore.